Dissociating of water. So here we have two water molecules. We've got one with a green hydrogen. That proton is going to be given to the other water molecule. So we've got this one. Change my color here. We've got this one. It's going to give its hydrogen away and become a hydroxy. And we've got this one that's going to gain a hydrogen. So that makes this one a base, but the other water is acting as an acid because it's giving its proton away. And here we've got the conjugate acid and the conjugate base. We can write an equilibrium expression for this, and for that we would put our products on the top. So we'd have our H3O and we'd have our hydroxy, and on the bottom we'd have water and water. Now there's a problem with this. These two waters, the reaction is taking place in water. There's so much water that the concentration of water isn't going to change. And so that's going to be irrelevant. And so the equilibrium constant is going to be equal to the hydronium concentration times the hydroxy concentration. And as I've been saying, it's a constant. So it's equal to 1.0 times 10 to the minus 14th. So the concentration of these two in pure water will always be equal to 1 times 10 to the minus 14th. So we can use this equation right here to calculate the concentration of hydronium if we're given the concentration of hydroxy. So let's look at the hydronium concentration in coffee. We're right down here. We've got an equilibrium constant, or a dissociation constant in this case. It's equal to 1 times 10 to the minus 14th. The hydroxy concentration was given to us. It's right here, 1 times 10 to the minus 9th, and we don't know the concentration of the hydronium. We do know that Kw is going to be equal to hydronium concentration times the hydroxy concentration. We can solve this equation for the hydronium concentration, and we'll get Kw and divide it by. All I've done is rearrange that algebraically. You can prove to yourself that if you divide both sides by the hydroxy concentration, it drops off one side and appears on the bottom of the other. So then we can just substitute in. We've got 1.0 times 10 to the minus 14th divided by 1.0 times 10 to the minus 9th. And this is going to be equal to 1 times 10 to the minus 5th molar. This is a good time to get out your calculator and make sure you know how to put in these exponents. If you'll use the E button to put these numbers in, you won't have any trouble with making sure that you're dividing by the whole number. Okay, so let's look at what's the hydronium concentration in soap. Well, Kw is always going to be equal to and we have this number, and we have this number, so we can solve for the hydronium concentration. It's going to be equal to Kw divided by the hydroxy concentration, and 0.10 to the minus 14th divided this time by 1 times 10 to the minus 6th. 1 times 10 to the minus 8. And that's a mole. Lemon juice would be similar. 1 times 10 to the minus 14th divided by the concentration here, which is 1.0 times 10 to the minus 13th. And we get a concentration up. This is actually, should be a 4. And we get 2.5 times 10 to the minus 2nd. Okay, so let's look at, see how these hydronium concentration affects whether things are acidic or basic. So you would expect that if things are going to be acidic, they're going to have lots of hydronium, and that's true. And so if the hydrogen ion concentration is greater than 1 times 10 to the minus 7th, then it's acidic. If it's equal, then it's neutral, and if it's less than, it's basic. So if we look at the hydroxy concentration, if it's less than this magic number, then we consider it acidic. If it's equal to 1 times 10 to the minus 7th, it's neutral, and if it's greater than, it's basic. So we can look at different solutions and decide whether we think they're acidic or basic. And I believe these are supposed to be 3s. They wouldn't have that plus there if they weren't supposed to be 3s. Okay. So let's look and see whether we think these are acidic or basic. So this number is 1 times 10 to the minus 7th. 2 times 10 to the minus 5th is larger. Remember, with that exponent here is a smaller number, it means that it's going to be closer to 0 and larger. So it's larger, and so we'd expect it to be acidic. 10 to the minus 9th, however, is smaller than our 10 to the minus 7th, and we expect this to be basic. Or it is basic, I guess we should say. For this one, let's see, 12. We're looking at, let's look at this, just this number. This number is smaller, and so we'd expect this to be basic. And this number is larger, and we expect it to be acidic. You have to remember that very small numbers have larger negative exponents.